Hello everyone, welcome back to my YouTube channel, and in this video I'm gonna talk about complete binary tree data structure. And let's see what is a binary tree. A binary tree data structure is a hierarchical data structure in which each node has at most two children referred to as the left child and the right child. Let's see the picture here. And there is a root node and 2 and 3 are root nodes children. Like that, in this binary tree, not only this binary tree, all binary trees, there are parent nodes and children nodes. We represent each node of a binary tree by an object which stores elements and references to its parent and children nodes. And let's go to the main topic. What is a complete binary tree? A complete binary tree is a binary tree that satisfies following two properties. First one is, in a complete binary tree, every level except possibly the last is completely filled. Look at the picture here. In this picture, every level except this last level is completely filled with nodes, and all nodes appear as far left as possible. Means every node except leaf nodes has a left child definitely. If any node except leaf node doesn't have a left child, then it's not a complete binary tree. So I think you have a brief idea. In a complete binary tree, if you want to know how many nodes a level can have, you can use 2 to the power r formula, where r is the level of the nodes. And in this example picture, you can see, let's see how many nodes can level 3 have. So, using 2 to the power r formula, where r is 3 here, we can see 2 to the power 3 is equals to 8. So, in this binary tree, in the level 3, we can have maximally 8 nodes. And since this is a full binary tree, I will explain what is a full binary tree later. There are 8 nodes in level 3. Let's talk about full binary trees now. What is a full binary tree? You can see the same image as before here. This is a full binary tree. So what makes this a full binary tree? A binary tree is a full binary tree if and only if each non-leaf node has exactly 2 child nodes and all leaf nodes have identical path length. So you can see in this picture, every parent node has a left child and a right child. So, except leaf nodes of course, and all leaf nodes have identical path length. So here 8 is a leaf node and 8's path length is 1, 2, 3. And same as the 14 is also a leaf node and the 14's path length is also 3. So this is a full binary tree. And there is a catch I want to mention. Every full binary tree is a complete binary tree because every node has a left child except leaf nodes. But not every complete binary tree is a full binary tree because there can be parent nodes which doesn't have right children in a complete binary tree. Now, let me walk you through this Java program that checks whether a binary tree is complete. I start by defining a node class to represent each element in the binary tree. Each node consists of three components: an integer value called data, a left child, and a right child. In the constructor, I initialize the node with a given value and set both child references to null. This allows me to easily create new nodes when building the tree. Next, I created the binary tree class, which contains a root node as the starting point of the tree. The most important part of this class is the isComplete method, which determines whether the tree follows the rules of a complete binary tree. The first thing I check is whether the tree is empty. If root is null, I return true immediately because an empty tree is technically complete. To process the nodes efficiently, I use a queue and apply a level order traversal technique, also known as BFS. I start by adding the root node to the queue and introduce a flag called foundNull, which is initially set to false. This flag helps me track whether I have encountered a null node during traversal. Now I process nodes one by one using a loop. I remove the front node from the queue and check if it is null. If I find a null node, I set foundNull to true. This means that all nodes after this point should also be null for the tree to be complete. If I encounter a valid node after finding a null, then the tree is not complete and I return false immediately. For every valid node, I add its left and right children to the queue, even if they are null, to ensure proper level order traversal. If I finish the traversal without detecting an incomplete structure, I return true, confirming that the tree is complete. Now, in the main method, I created a binary tree with the following structure. You can see the structure in this picture. This tree follows the rules of a complete binary tree. All levels are fully filled except the last, and the last level is left alive. I call the isComplete method and print the result. Since this tree meets the conditions, the output should be true. This approach is efficient because it runs in O(n) time complexity, meaning it processes each node only once. By using level order traversal and a queue, I can systematically verify whether a tree follows the rules of completeness. This method is commonly used in data structures like heaps, where maintaining a complete binary tree is crucial for efficient operations. Okay, here is the code I explained you earlier, and let's see whether the code is running without any errors and is doing what it's supposed to be doing. Okay, for more information, this is the tree we created before, I explained you earlier, and let's run it. Okay, here is the output. There is a string, is the tree complete, and question mark, and the answer is true. This is a string and this is a boolean output. According to the output, the tree we created is a complete binary tree. And I forgot to mention, I created this Java program using NetBeans IDE. Now, let me explain how can I construct a complete binary tree using an array. Instead of using nodes and pointers, I store elements directly in an array based on their level order positions. In this program, I first created an array-based tree structure with a fixed capacity. The insertion follows a simple rule. I place each new element at the next available index, ensuring that the tree remains complete. When inserting elements in order, the structure will look like this in the array. This corresponds to the following binary tree. You can see the picture here. Notice that every level is filled except for the last and the elements are added from left to right, exactly following the definition of a complete binary tree. When I run this program, it prints the tree as an array, making it easy to visualize and store in memory efficiently. That brings us to the end of this video on complete binary trees. I covered the definition, properties, node arrangements, and how to identify complete versus incomplete binary trees. I also demonstrated how to check if a binary tree is complete using Java and how to construct a complete binary tree using an array representation. This video is mainly for a university project, so the focus was on presenting the concepts rather than in-depth teaching. If you found it useful or have any suggestions, feel free to leave a comment. Thanks for watching, and special thanks to Soorya Rajakaruna for editing this video. Stay tuned for more content. Thank you.